Assalamu alaikum. In this lecture, we will see how the operating system can give the illusion of running multiple processes simultaneously on a single CPU. It's definitely not magic, it's rather science. In the chapter, we will address the basic concepts of scheduling, what criteria are there in scheduling algorithms, different scheduling algorithms. The rest of the chapter is not for you. So what are the main objectives of the chapter? Is to introduce the main concepts of CPU scheduling and what are the basics that we need to address to allow multi-programmed operating systems, and to describe various scheduling algorithms. As I've said, the rest of the chapter will not be addressed in this course, but I highly recommend that you go and read it because there are really interesting things there and it will add lots for you, and not only in how operating systems are designed, but also in how to think of solving different problems in life. What are the basic concepts? Simply, one of the objectives of designing an operating system is best utilization of resources. So to maximize the utilization of the CPU, we need not to let it stay idle for long times. Generally, any process while executing will be alternating between two states. It's either using the CPU or it's waiting for input-output operation or a signal or whatever. We will call this bursts, a CPU burst and input-output burst. So any process while executing will be exactly doing this, using CPU, then using input-output devices. Let us assume a simple code that adds the value of two numbers and print it out. So when you run it first, it will be executing in the CPU, the parts where you declare the variables, and then when you come and need to read the values of the variables, the two variables that you are adding, x and y. So read x, this won't be executing in the CPU. You will go and read from wherever you are getting it, from the keyboard, or from a file, whatever. And then you will read y, and this also will be input output. Then the addition part will be running in the CPU, and the printing part will be an output. So even the simple, you can see this in the simplest form of code. While the process is waiting for input output, why should we allow it to be in the CPU while other processes are lining in the ready queue, waiting for the CPU to be free? Why should we leave the CPU idle while other processes are in need of the CPU? Usually, if we looked at how a process will be behaving in terms of the CPU, it will look just as this diagram. This histogram will show you how the normal process behavior. A process will have a very small CPU first, and then it will wait for long times for input-output operation, because the CPU is the fastest part of the computer, mainly. Most of input-output peripherals and the hard disk are much slower than the CPU. The response time is longer than the response time of the CPU. So it's the job of the short-term scheduler to provide the maximum possible utilization of the CPU by not allowing a process that is in an input out first to occupy the CPU, the first and foremost. In this case, we are talking about non-preemptive scheduling algorithm that will not force a process out of the CPU unless it does not need the CPU at this time. There are actually, as we have said earlier in the last lecture, that there are two types of scheduling, that is preemptive and non-preemptive. In non-preemptive, the process will only be taken out of the CPU if it does not need the CPU or it did finish execution. The CPU scheduling will be taken in three different conditions. If a process is switched from running to waiting. A process was running on the CPU, now it's waiting for an event, input-output operation, signal, whatever it is waiting for. When a process is switched from running to ready, if a process was not ready, and now, why did I miss this? If a process switched from running to ready, if a process was running and now it was actually forced out of the CPU, so now it's ready. Or if a process switched from waiting to ready. ثلاثة 3 times we will take the decision. First, imagine the CPU is empty. So a process is ready. There should be a decision which ready process will go into the CPU. That's when the CPU is empty. Then, if a process that is running in the CPU has changed its status from running, now it's waiting. Or a process that was waiting has finished waiting and it's ready. Or if a running process was forced out of the CPU and back to the ready queue, there should be a decision taken which processes from the queue will be in the CPU. One, or when a process terminates. Can be status 1 and 3 and 4. Sorry, 1 and 4 are non-preemptive scheduling. That means the process won't be forced out of the CPU unless it does not need it. it's waiting, or it has finished execution. Two and three are different cases because the process can be switched from running to ready. It's running. It still needs the CPU. Like it can be forced out of the CPU. Or if a process that is not, if a process is running and another process became ready, the new process can force the old process out of the CPU. These are for sure preemptive cases. With preemptive scheduling came the problems that we discussed some of them in the past lecture. What about shared variables? What about preemption while the process is in the kernel mode? And how can I handle interrupts that happens through crucial and critical operating system activities? After the decision is made, which process will be running, will be changing its status from ready to running, or from running to ready, or from running to waiting, and now it will be forced out by the short-term scheduler. Another part of the operating system that we call the dispatcher will pack the process that was in the CPU, store all its information in its process control block, and unpack the new process, get all the information from the process control block and load it into the CPU. This we call context switching, where we switch the context of the CPU. And this process takes time. This time we call the dispatcher latency. And this context switch time, we consider it to be an overhead to the CPU. It's necessary, it cannot be avoided, but it does not count in the time that we actually utilize the CPU.